Thank you all for joining us for our Caltech Astronomy Stargazing Lecture, the first of the 2026 season. We've got a very special show tonight, so thank you all for joining us. I'm Dr. Cameron Hummels. I'm the MC of these events, and I'll be your host tonight. So I'll just kind of lay out our schedule for tonight and then introduce our speaker. So these events happen one Friday night a month. They've been going on for 10 years now, and our next one will be, I don't remember, it'll be at the end of February on a Friday night. I'll announce it in all the usual places. So however you found out about this event, you can go back to that place, whether it's social media or the Caltech calendar or whatnot, and find out about next month's event. So how tonight will go is I'll introduce our speaker in a few moments. He'll speak for roughly 30 minutes about this amazing topic and show some really awesome computer visualizations of different astrophysical objects and how they form and change over their lives. And then we'll have a brief Q&A session with all of you for 5 or 10 minutes. And then we'll have a brief intermission, and you'll have kind of a choice to make. So in this auditorium after that intermission, we'll continue to take questions from the audience. It'll be our speaker, myself, and 2 other members of the department to handle questions that you throw at us about every manner of thing, related to science. Astronomy, physics, space science, maybe something you read in the newspaper about physics or astronomy, maybe something that you saw on YouTube or whatnot, and we'll try and address whatever questions you may have. At the same time as our Q&A panel here, we'll have telescopes set up in the fields directly behind us, and so you can go out the front door and follow the signs, a couple hundred feet to the fields behind us. And we have 3 telescopes set up, and you should be able to see tonight. It's actually pretty clear despite the clouds today. Right now it's clear. We should be able to see Jupiter, should be able to see the Pleiades star cluster, and either the Andromeda Galaxy or the Orion Nebula. And feel free during that hour or so after the presentation's done to, if you see all the things through the telescope and you're like, I'm done with that, come on back in and ask questions of our Q&A panel or vice versa. So both will be going until about 9:45 or so. And then it's the end of the night. So in addition to these series of events, we have another series that takes place in Old Town Pasadena, just a couple of miles from here, called Astronomy on Tap. These Astronomy on Tap events are like these, but a little less formal, because they're in a bar. They're in a beer garden, an outdoor beer garden called the Doghouse, and they feature 2 15-minute or 20-minute public presentations on science, much like we'll hear tonight, but on different topics, and a little, as I said, a little bit less formal. There's also astronomy-themed pub trivia. There's telescopes at that. We've also started bringing VR headsets, so you can see different astrophysical phenomena through the VR headset, which is pretty cool. The next one of those will be Monday, February 9th. And I should have the poster out for that on Monday. So stay tuned on that. I should also mention that Caltech is helping to put on the Death Valley National Park Dark Sky Festival this year, which is also in 2 weeks' time. That'll be 2 weeks from today, February 6th, 7th, and 8th at Death Valley National Park. So we're partnering with the National Park Service and with NASA JPL and NASA Goddard, NASA Ames, some other institutions to help put on this event. It's free, you just have to get into the park. So if you have a parks pass, then you're golden, but if you need to pay, it's, I don't know, like $30 per car or something like that to get into the park. And over those Friday, Saturday, and Sunday, there will be a number of different events happening. Each night there will be star parties with lots and lots of telescopes set up, so you can take advantage of the really beautiful night sky that's in a place that's much lower light pollution than here in LA County. But there will also be public lectures given by, I'm actually giving one, and colleagues are giving them. There will be an astrophysicist Q&A. There will be astronomy on tap events that we're doing at the bars in Death Valley National Park. So there's field talks where you go out in like the dunes, and a scientist talks about how the dunes or other features in the park are similar to planetary analogs elsewhere in our solar system. So it's a really cool opportunity, and it's virtually free. So if you're interested, I encourage you to check it out. I posted it on our social media and on our website with more information, including the schedule. So check that out. I think those are all my announcements. So, took notes because Phil, our speaker tonight, is really an esteemed individual. I can memorize all the things, but so Phil Hopkins grew up in Ohio before attending Princeton to do his undergraduate studies in astronomy and physics. Then he attended Harvard and earned his PhD there, and then went to UC Berkeley, had a prestigious Miller Fellowship as well as an Einstein Fellowship before he was then hired here in 2013 as a faculty member. He's now the Ira S. Bowen Professor of Theoretical Astrophysics, but he's had a number of different accolades over his long career, an NSF Career Grant, a Bach Prize, a Helen B. Warren Prize through the AAS, which is basically goes to the best junior astronomer in the country doing a junior, not like he's a little guy or anything, but junior level faculty member. So in the first 5 years since he finished his PhD, this is awarded to one person. Sloan Research Fellow, and then recently the High Energy Astrophysics Mid-Career Award. What's really notable about Phil is he does it all. You know, he works on a number of different topics, from some you see here: galaxy evolution, star formation, planet formation, cosmic ray transport, astrophysical turbulence, cosmology, so many different topics, the nature of dark matter, so many different topics, and has made significant contributions to all of those. He is the PI of a code called the GISMO code, which is what is used for the generation of many of these simulations that he's going to talk about. And for anybody who's a software developer, it's knows how difficult it is to keep a publicly maintained code that has, you know, dozens of contributors and hundreds of users across the entire field. It's a huge amount of work. He continues to put out an enormous amount of papers. Just for reference, when you're doing a PhD in a physics field or astronomy, oftentimes as a student, you might have a few papers that you put out as a first author, maybe 3 or 4 or 5. Phil had 26 first author papers as a graduate student, and since that time, total first author papers has 130, and his H-index is 155. He's very, very productive. And oftentimes, colleagues and myself wonder how he's able to find the time to do all of the work that he does. I'm convinced that he has a time turner, like people have in, like Hermione has in the Harry Potter series, where he's able to travel in time and get more time out of the day, because I really don't know how he finds the time to accomplish all that he does with a family, with twins. It's incredible. So please welcome a very good friend of mine and one of my favorite people, and one of the people that I think is one of the smartest people working in astrophysics, Professor Philip Fajardo Hopkins.
Well, thank you so much. I don't know how I'm possibly going to live up to that introduction. I will try my hardest to entertain and convey some cool information and if nothing else, animations and exciting developments that we've all been working on. And at least part of the answer to Cameron's question about productivity is that I've been very fortunate to work with a really fantastic group. The names here are just some current and recent students that I always make a point to shout out, the students who are like applying for jobs right now. So these just happen to be those students, but many current and former collaborators, a couple in the audience, former collaborators, and Cameron has been a collaborator since we were friends as grad students through our entire careers, basically, especially the last decade or so that we've both been at Caltech. So I'm going to focus on one thing and try to give you a sense of sort of how we think galaxies are made, and more than how they're made, what I want to try and give you the impression of in this talk is that you know, things like galaxies and the cosmic web, which I'll tell you what that means in a minute if you're not sure, we often think of as these static things because they're evolving over timescales that are truly staggering and incomprehensible to us, right? Billions of years is not something that we can just visualize. It's not something I can visualize. But But it's why we can do things like computer simulations where we can make that happen in a matter of minutes, right? Accelerate those billions of years to minutes and get a real picture for, when you see it happening on these human timescales, you realize that these systems are really dynamic, chaotic, energetic, exciting, evolving systems. And they're not these sort of static, atrophied things that I think we often imagine them. And as scientists, we used to think they were, actually. So to start, let me actually take a step back and define some terms that I'm going to use, and hopefully the audio here works. So hopefully people can hear this. It's the Monty Python Galaxy song. So that's us, and that's the sun. When I say stars, I mostly mean things like the sun. And our whole solar system is part of this giant galaxy, right? So our solar system around the sun is orbiting our galaxy. This is a picture of Andromeda. We can't go outside our own galaxy. Let's take a picture of it. Contains 100 billion stars. It's 100,000 light years. That's a size scale, which I don't expect you to actually internalize. That's the center, the bulge. 30,000 light years from galactic central point. We go around every 200. So this was the last lap of the galaxy. What was happening on Earth was dinosaurs. And song says, there's millions and billions of galaxies. There's 100 billion galaxies in the observable universe, and ours is a typical one. These are images of galaxies from the Sloan Digital Sky Survey, a real astronomical survey, in the universe today, where it's almost 14 billion years old. And it's, space is very big, so in case you're wondering, we're moving at 400 trillion times the speed of light to fly around like this. In all of those directions it can whiz. And this is expanding and growing in time. The speed of light, 12 million miles a minute, and that's the fastest speed there is. So remember when you're feeling very small and insecure, how amazingly unlikely is your blood. And pray the dense intelligent life somewhere up in space, cause there's bugger all down here on Earth. All right, so there's your very quick primer on what a galaxy and a universe and a solar system is, if you needed a refresher. And that's just what we can see with our eyes or with telescopes to aid our eyes. But it's also worth noting that there's a lot of what we know and a huge amount of information, and a huge part of the universe is not what we can see with our eyes, but light that we can't see so easily. So for example, here's a famous galaxy, M82. It's one of the most famous galaxies for people like me who study how galaxies form and evolve. And this is its image with a typical telescope in visual light. And it's pretty boring, frankly, in visual light. It's not that spectacular. It's not one of the beautiful Hubble images you're used to seeing. But when you look at it at other wavelengths of light, it suddenly becomes spectacular. So this green part in this image, composite image from NASA, is the visible light from the stars in the galaxy. But then there's this stuff coming out of the galaxy. The blue is X-rays, which is really, really hot gas, millions of degrees Celsius or Kelvin. And the red is really cool gas. It's basically dust and it's interstellar soot, sort of ash from exploded stars, which is what contains a lot of the heavy elements and ultimately builds things like planets and us. So on top of that, there's, of course, we think, a huge amount of other stuff that we can't see in any type of light, which we call dark matter, because it's not producing any type of light at any wavelength. It's not producing radio or X-rays or any other type of electromagnetic radiation. And we think that our galaxy and all galaxies are embedded in these giant, we call them dark matter payloads that extend 10 to 100 times the size of the galaxy out into intergalactic space here around. So how do we get this? What's the sort of recipe? How do you try to make a galaxy? How do we understand how a galaxy is made? Well, we have those basic ingredients that I just described. So there's sort of gas and dust, which are based on equations of fluid dynamics. There's dark matter. And we have some idea of what the early universe before galaxies looked like. This is an image of what the whole sky looks like according to the Planck satellite. This is looking at what's called the cosmic microwave background. It's the radiation left over from shortly after the Big Bang. And basically these little patches of different colors are just tiny fractional variations, right? It's a tiny fraction of a percent brighter or denser in one spot and a tiny fraction of a percent brighter or less, fainter or less dense in other spots. So the universe was very smooth, but it had these little ripples. And there's whole fascinating questions about how we got to this point. You wanted to, if you read about things like the Big Bang and inflation and all of this, but I'm going to pick up where we're well after this point, where we're trying to make things like galaxies and stars. Okay, so this gives me something like what the universe looked like when it was about 400,000 years old. And we want to know how to get from that to nearly 14 billion years old. Well, the dominant force on these large scales in the universe is just gravity. It's gravity that tries to pull things together. And the equation for gravity is actually very simple. We don't actually need to worry too much about things like relativity and all of that. I can make it more complicated if I wanted, but it doesn't really matter for anything I'm going to say. So we can just use Newton's law of gravity, which is that the acceleration, how fast something's velocity changes of something, is just proportional to some constant times its mass divided by the distance squared between any two bodies. And we can represent this with a whole bunch of little blobs of dark matter and gas and things like that, and just solve this equation over and over and over again. It's a very simple equation. We just need to solve it between a ton of different interacting bodies, and we need to solve it like 1 trillion times. And computers are really good at that, right? Giving them a simple equation to just do brute force over and over and over and over and over again. So that's basically the heart of the kinds of simulations our group does, is iterating those simple equations over and over to get from those initial conditions to some later time. So what does that look like? Well, here's an example of one of these simulations, and I'm showing it in the box is kind of scaled so that the overall universe expanding is kind of factored out, because otherwise this would be a boring movie, because it would just start like a point and like flash to bigger than the screen, and you wouldn't be able to see any of the action. So think of it as our cameras expanding or shrinking to follow things. What you can see is by these late times, this Z means it's an astronomer shorthand for what we call the cosmological redshift. If you're not familiar with that, just think of it as a countdown to present day. High number means early times in the age of the universe, and it's just counting down to present day. And as time goes by, what we see is this initially very smooth distribution of matter starts to clump up. And that's just gravity. Gravity pulls things together, right? Gravity wants to take things and combine them and make them denser. And so a little ripple that's got a little extra mass in one position will have a little more gravity than a patch next to it that has a little less material. So it'll pull stuff towards it, net. And that means the imbalance will increase, right? Because then that patch will have even more material, and the other patches it grabbed from will have even less material. So it'll get even stronger in its pull. So it's a runaway process. As it starts pulling together, it runs away and starts collapsing all the mass into these dense little nodes here. This whole structure we call the cosmic web. We've got these filaments and things connecting these little nodes, and each of these little bright spots, these nodes, we think is the site where the material can collapse and get dense enough that could form a galaxy. So each of these little tiny knots would be a galaxy. And in 3D, when you fly through that at present day, this is a visualization of that same simulation showing the sort of cosmic web that you get in 3D as you fly through it. So again, each of these knots will have a galaxy. The bigger, brighter ones have more material pulled together, so they presumably form bigger, brighter galaxies. And the smaller, fainter ones have less material, so have less fuel, so would form smaller, fainter galaxies, because there would be less stuff available to form stars in those galaxies, so you'd have less stars in them, and they'd shine less brightly. And if you compare this model, if you just paint a galaxy on every one of these blotches, this actually agrees spectacularly well with measurements we make, where we go out and do roboticized surveys nowadays, where we find every galaxy we can on the sky. and we catalog how far they are away and what their positions are. If you look at the distribution of galaxies, where they are, when they are in the sky, this really gives us a great sort of backbone on which we can understand where galaxies are and how they got to be in those places at those times. This sort of large-scale distribution looks great compared to what we measure and observe. That's all I'm trying to say. But when we actually look at the galaxies themselves, that's where more questions come up. So the idea basically is if gravity was the dominant force, we can sort of just iterate this over and over all the way down to planets. And the idea is that you have some blob that we started from. That's the whole visible universe, the box I was showing you. And within it, material has been pulled together by gravity to form one of those nodes. Within that, material gets pulled together by gravity to form a galaxy. But even within the galaxy, gravity's still going to keep pulling stuff together. So gas and dust within the galaxy gets pulled together to form things like what we call giant molecular clouds, clouds of molecules that get denser and denser. And within those clouds, gravity will pick out the denser regions and pull more stuff towards them. And they'll give you little clumps that contract until they eventually get so dense that the atoms inside are banging together so hard that you ignite nuclear fusion, you get a little nuclear fusion reactor going in your dense clump of gas, that's a star. So it lights up as a star. And around that star, smaller clumps that don't have enough material to get that nuclear fusion engine kick-started become things like planets, once gravity's pulled them together as far as it can. And so this would just sort of cascade down, gravity just pulling things together every step of the way. And again, this is basically the cartoon version. Gravity pulls you in, your gas might heat up. At a little more detail, you might ask, like, why do galaxies kind of look like they're spinning or twisted, these spiral arms? That's just because of this principle of, in physics, angular momentum conservation. It's the same idea as, why do you spin faster when you pull your arms in if you're a figure skater? Or, everybody's probably had some version of it. If you're spinning a rope around and you shorten it, it'll start going faster. Those kinds of principles, just as this material falls in, if it's got any little bit of spin, it'll spin faster and faster as it contracts down and gets crushed down. So it'll just start spinning rapidly. And that would explain why you get this sort of stuff swirling around the stars or swirling around the galaxies. And that stuff swirling around inside the galaxy, we call the interstellar medium. It's not a creative name, it literally just means the stuff between stars. So, and you can, again, like I just said, you can imagine this process iterating. So here's another simulation of the sort of following stages of this. You've got gas inside of a galaxy, and gravity in this is pulling it into these filaments, and at the nodes of these, you've got like a little blob there that gravity is pulling more stuff together in, and it's going to start igniting a star. This will zoom in to the material right around the heart of that collapsing star, and actually you'll see in this movie, there's a little overdense blob in this swirling disk of material that collapses and will form a sort of Jupiter mass planet around that star. The same kind of process is really happening on all of these scales, basically. There you go, got a couple of lumps. One of them will form a planet, the other one I think gets sort of torn apart there, actually. But this isn't the whole story, basically. And this is the real central problem in understanding things like how galaxies form has been that we know that this isn't the whole story, and we know that this is very incomplete, and actually gives a pretty bad description of the universe if this is all that we do. And there's many ways I could show this, literally thousands of different types of measurements of myriad different things, millions of independent data sets and data points. But I'll just show one example, which is if I make a prediction for what the galaxies around a galaxy like the Milky Way should look like, if gravity wins, it should look like this thing on the left, where every one of these blobs is a massive bright galaxy that we should be able to see in the night sky. In reality, there's only a few massive bright galaxies in near proximity to the Milky Way, and in fact, there's only two that can be seen, that are bright enough that they can be seen naked eye by humans. The Small and Large Magellanic Cloud, if you're in the southern hemisphere, be familiar with them. Has anybody in the audience seen personally the Magellanic Clouds? A couple folks. It's really cool if you get the chance, if you're ever in the Southern Hemisphere. You can say you've seen another galaxy just by eye. But there's, you know, even with telescopes, there's only a few of these little galaxies around us. There's not hundreds and thousands the way this predicts, if gravity was able to pull everything together. And again, I could give you lots of other examples of where it becomes clear that gravity can't be the end-all be-all of the story. Now, at the risk of overstretching an analogy, I'm going to make an analogy for the remainder of this talk of this to the Avengers here. And specifically, I'm going to cast gravity here in the role of the villain. So we got gravity's Thanos here. He's trying to crush everything with his infinity gauntlet. And this is the version where he wins. And reality is, you know, disappointed Thanos. So why, you know, didn't gravity win? Well, the simple answer is because things like stars, when you start making them, do stuff. You just turned on a runaway nuclear fusion reaction, that's got to do something, right? And it does. After all, stars do things like shine, right? That's how we see them. That's what literally astronomy is named for stars, because we see stars. And stars shine like our sun. We know that shines, and it's pretty bright to us. But our sun's actually pretty puny by the standards of how bright a star can shine. There's much brighter stars that we call things like O stars, massive stars that can be millions of times brighter than our sun. That are giant blue stars that really blow up. And we can see their radiation just directly. We can even see its effects on the medium. This is a time lapse of radiation expanding around the star. We call it the light echo of that star here. So we've got radiation pushing out, and this can heat up the material around the star, can shine and do things like ionize material. It can heat it up, it can push on it. Light actually can push on things if you hit it hard enough. We do this in the lab with lasers, and it happens in space all the time. So, so one way that stars can fight back is by shining or emitting radiation. So I'm gonna call that Thor, because, you know, lightning. So that's one of the ways that stars can fight back. And by the way, this was to say, I couldn't show the O star to scale in brightness or size, because if I did, this would be just a small piece of what the O star looks like on the screen here, if I tried to show it to scale. I'd be blinding you all and need, you know, 1,000 times bigger projector here. Another thing stars do is that they blow material off of their surface. They have winds, they're launching stuff off of them. There's energy being generated by these nuclear reactions is launching stuff off the star, and the sun is doing this all the time. It's what we call the solar wind. And this is real movies from the Soho Observatory of the wind coming off the sun. This circle is just a mask so that the light doesn't get, you know, it doesn't blind the detector by just looking directly at the sun. You can see this material shooting off of it. So these are basically giant launches of material, pressure waves and things like that. So I'm going to call that the Hulk, because it smashes stuff and launches stuff. And then stars also explode. So these are supernova explosions. So it can happen in many different ways. A very massive star at the end of its life can explode, but also a star with a companion can eat material from it until it overeats and causes itself to explode. Basically, that reaction runs away, and instead of a nuclear reactor, it becomes a nuclear bomb and explodes. And those explosions, those supernova explosions, are certainly seen. There's famous nearby examples of the relics of supernova explosions. This is the Crab Nebula, which is studied a lot in astrophysics. That was a historical supernova. Chinese astronomers noted when that star exploded, and we saw it from Earth in 1054 AD. And we still see its remnants spitting out. That's the leftover junk from that star. We see them happening in nearby galaxies. This is that same M82 galaxy that I said didn't look very pretty in the optical. A few years ago, 10 years ago, there was a supernova in it. We did observing nights here to look at the supernova. And the point is that one supernova, for a brief period, you know, of a few days or so, was bright enough that, you know, this isn't like artificially enhanced. That bright spot compared to the whole rest of the galaxy was that single supernova explosion. You could see it through a telescope pointed at the galaxy. So it was as bright as something like 100 billion stars for a very brief moment in time. Now, these explosions can inject a tremendous amount of energy. They're also responsible for most of all the heavy elements in the universe. They dump all this material out that was burned in the star, and so they're responsible for the carbon and oxygen that makes us up. So I'm going to call them Iron Man because that's where the iron comes from. So what we try to do when we model all of this is to put all of these effects together into a single computer simulation that tries to incorporate it all. So this is from some simulations called, a project called STARFORGE, led by some former Caltech graduate students, who are simulating, these colors are showing the gas and dust swirling around one of these clouds in this interstellar medium. Those white spots are stars. You can see things like those bubbles that are created there, those are the radiation zooming out. These little columns, those are jets, those are like winds, but sometimes stars can launch these very narrow plumes or jets of material. If I have to give that another name, I guess I'll go with Hawkeye for those, because they're kind of arrow-like. The winds from the stars carve some of the other outflows. You can occasionally see, it's a little harder to contrast, you can see some of these sort of hollow fronts moving out. And if we evolve this for long enough, unfortunately, this particular movie, it's a stunningly beautiful movie. There's a supernova that happens off screen, and the screen will rotate back, and you'll see there's kind of a hole in the gas where the supernova has exploded and swept everything out of some huge chunk of the cloud from which these stars were forming. And you can see them, interacting constantly, interfering with the medium. There's that giant hole. There was a star that exploded in the middle of that hole, basically, and carved that giant bit. And we see things like this in real regions forming stars. These are images from different space telescopes, looking at combinations of infrared and visual light, and you can really see things that look very similar. Stars carving these giant holes in the gas as this material gets shoved around and pushed back on and launched back out. So let's zoom back out. Let's work from sort of small scales back up to large. So we've got these explosions. So let's think about if this is happening in one little region forming stars that I was just showing you. Let's pan out to a whole galaxy, and you've got these little pops of energy and winds and explosions happening all over the galaxy. And they can start to add up all over the whole galaxy into a huge amount of material being launched out of the galaxy and sort of re-energized. And again, we see this. So again, this famous image I showed you early on, why does this galaxy have all this stuff coming out from the part where there are stars? Well, it's because in that very central region of the galaxy, there was an episode that it formed a bunch of young massive stars, and then a bunch of those stars exploded. So in the last relatively recent time, as far as these things go for galaxies, the last, say, 100 million years, it's had something like 10 million supernova explosions all explode inside of that circle. And the energy from all of those is what's launching all of this material out of the galaxy. That's something like 1,000 miles a second out from the center of the galaxy. So it's really able to beat gravity and launch stuff back out. And when we put that together one step further and zoom out, you get something like what I'm showing you here. So this is from our related simulation project that we call FIRE. This is sort of simulating whole galaxies and their evolution, trying to model all of this. And it's just a galaxy that will, by present day, look kind of like the Milky Way. Remember that Z is just counting down to 0, which is present day. So in early times, you can see that things are kind of a mess. The starlight looks like a mess. And if we could look at all the gas, the fluids, the dust, it all also looks like a mess. And there's a bunch of different stuff. I tried to label this by the phases or the temperature of the material, and there's a huge range. You can see, astronomers sometimes, our scales are wonky, right? The cold gas, okay, it's very cold. It's, 10 to 100 degrees above absolute 0 or so, so negative a couple hundred degrees Celsius. We like to say gas is warm when it's, a balmy 10,000 degrees, right? And to be proper hot, you need to be billions of degrees, basically. But you can see that material in early times is kind of exploding and churning and mixing around. And then finally, at later times, it sort of calms down a little bit. And gravity partly is starting to win more at these later times. As the system gets bigger and bigger and more massive, gravity is able to beat more and more of these explosions trying to blow stuff out of the galaxy, and things look a little more orderly and relaxed. And we see something that looks a bit like a galaxy today, but even then, chaos abounds, and another galaxy gets eaten and decides to sort of come in and smash into our galaxy here. And the timing's not perfect. This is about the mass of what we call the Large Magellanic Cloud, the bigger of those two Magellanic Clouds that we can see by eye. Ours hasn't yet smashed into us. It will in a couple of billion years, and then we're going to smash into Andromeda a couple of billion years after that. So this is already a lot of cool stuff that's happening and fighting back against gravity. But there's one more thing that I'm only going to mention in a couple of slides that also plays an important role in this, and that's also been the subject of a tremendous amount of study. But to see that one more thing, we have to zoom in all the way to the very center of the galaxy, to the very heart of the galaxy. So if you'll forgive me, I'm going to interrupt my Avengers metaphor and jump into my TARDIS so I can travel to the center of the galaxy. So here's us traveling to the center of the galaxy. This is a very trippy movie showing the flows and nature of the energy in the galaxy, giving you an idea, trying to give you a little more of an idea of the dynamicism of the galaxy as we're flying towards the center. And we start on the scale of the cosmic web of billions and billions of light years, and we zoom in all the way until we're something the size of the solar system at the very center, which then eats our TARDIS. And we can see things are very clearly sort of swirling around that central point. These lines are indicating the direction of flow of energy and material in the system. So what's happening there? Well, we see something like this in the center of our own galaxy. These are stars. These are real orbits of real stars. The lines aren't real, they're just connecting the measurements, but they're real orbits of real stars in the very center of our galaxy. And they're all orbiting around a common point. You just see by eye, all these stars are looping around some common point. But there's no star there. There's no visual object there. But whatever's there has to be tremendously massive and tremendously compact. What we can say from this is there has to be at least 4 million suns worth of material mashed into a space much smaller than the distance between the Earth and the Sun. And the only thing that really can exist at that massive a scale in that small a scale is a giant black hole. And we think now that basically every galaxy has a giant black hole at its center. Our galaxy's black hole is something like a few million times the mass of our sun, again, crushed into that small space. And we've even been able to take pictures of the material swirling right around the edge of those black holes in our galaxy and one other nearby galaxy with what we call the Event Horizon Telescope. So if you've seen the articles from a few years ago on the pictures of a black hole, this is one of them where we're imaging. Well, we can't directly see the black hole itself. The point of a black hole is nothing can escape, even light. That's this dark circle in the center. What we can see is the stuff swirling around the black hole that hasn't fallen in yet, past the point of no return. We call this the event horizon, where you can't get back out once you cross it. But the stuff swirling around can get incredibly hot and incredibly bright, and it can be swirling around at nearly the speed of light. So anytime a blob here slams into another blob, it can release a tremendous amount of energy. To give you a reference, nuclear fusion, which is what's powering the heart of the star, is one of the most efficient and powerful forms of energy we've ever conceived of and been able to realize. And that is very good at liberating a lot of energy. If I take the same amount of material that I would dump into a nuclear fusion reactor like the center of our sun, and instead dump it around a black hole, I'll get about 100 times as much energy out from dumping it into the center to a black hole. Before it falls in, if it slams into anything else, it'll emit about 100 times as much energy if I put it through all these nuclear fusion reactions, basically. It's a very efficient engine at creating energy, And as a result, these black holes can shine incredibly brightly when there's a lot of material swirling around them, when they're feeding actively. We call those things like quasars or active galactic nuclei. And these quasars are the brightest sources basically in the universe. And they can both shine incredible amounts of light, but they can also do all these other things I talked about, like blowing winds and launching jets. These are some famous examples of jets. Now we zoom back out. This is the scale of a galaxy again. This is a galaxy. And this is a jet of material launching out from the black hole in its center at nearly the speed of light, out to millions of light years, or 10 million miles from the central black hole. And the amount of energy is something like 1,000 trillion times the brightness of the sun is being generated by this black hole during this very brief episode where it's got lots of material feeding into it. So it's got a lot of power getting thrown into the engines. So to return to my Avengers analogy, I'm going to call this Captain Marvel, because she's not there very often, but when she does show up, she's completely overpowered and can basically take everybody out with one punch. And the black holes are like that too. So you add these things back in, and this is just that movie without the lines to make it a little easier to see, zooming in, but now what we have to include is that the very core of this thing is always churning and spouting out energy and jets and radiation, and all of these things we talked about earlier are coming out of that central region very powerfully. And when you do that, and you account for all that energy that can be liberated from this material swirling around the black hole, powering that engine, you can zoom all the way back out to the cosmic web on the largest scales and see how these things have a tremendous impact. So this is zooming all the way back out to the largest scales of the universe, the cosmic web. And it's showing a map of the temperature where the red is really hot material in the cosmic web. And these explosions, you don't have to worry about exactly what the colors mean to see by eye. There's just occasionally big explosions going off here at some of these nodes. Remember, the nodes are galaxies. There's the churn and the fight that the regular stars are putting up against gravity, but every so often one of them has one of these giant explosions. And those giant explosions are episodes where that black hole at the center of that galaxy gobbled up a lot of material. Somebody turned on that engine really fast, really hard for a short amount of time, and it generated this explosive injection of energy into the system that went all the way back out and launched material all the way back out to millions of light years away from the galaxy. And so if we come back to this picture I showed earlier of sort of gravity pulling everything down from large scales to ever smaller, crushing things down from the visible universe into galaxies, into clouds, into stars, into planets, this was our version of Thanos winning and crushing everything. But really, what we have is a much messier picture where all these small things fight back. And it's a classic, the harder that gravity crushes, the more you turn things into stars, the more you fuel the engines of stars and black holes. The more stuff gets into them, the harder they fight back. The analogy probably works best for Hulk. Basically, the harder Thanos fights, the angrier Hulk gets, and so he pushes back harder. So it's really a constant battle. And what those movies, if you get anything from them, what I hope they convey is that it's not a sort of calm, stable, steady system. It's a very dynamic system where it's going back and forth. Sometimes one side is winning, and you get these explosive events where everything gets launched out of the galaxy. And sometimes gravity wins, and everything falls back in. You get a giant burst of new stars forming, new black holes growing and gaining fuel. But it's a constant back and forth between those two. And so to conclude, I'll just put up a movie of one last fly through a galaxy today, like the Milky Way from these models, and I hope I leave you with the conclusion that this is chaotic and dynamic, but as a result of that, it's really fun and really wonderful. And if you want to look at more visualizations from our group or other people that I've just collected what I think are cool visualizations from, try to credit them, you can go to my website and try to collect a bunch of things there and link to them. Thanks everyone, and shameless picture of my twins in there.
Okay, we can take a few questions from the audience. Any questions for our speaker? We have a question, sir.
How do you add dark energy to the simulator if we don't know much about it?
That's a really great question, and that is the problem. We don't know much about dark energy or dark matter, for that matter, to add them in. So we add in what we do know, which is some of their measured effects. So we know that dark matter acts adding to gravity in certain ways, and we know that dark energy acts to stretch the universe and make it expand faster with time. And that's in fact how we measured that dark energy exists. We measured how fast the universe was expanding. So we can put that part in, but there's lots of ideas about what dark energy and dark matter really are. So one of the things that we try and do with these is say, okay, somebody has this idea about what dark energy or dark matter really is that makes more detailed predictions for what it should do. And we can model that on the computer, put that in, and then try and see, would that do something to all this stuff that we can see? Because we can't see dark energy directly, but we can see the galaxies that form. So if it would change the galaxies that form, then we can try and test those models. But it's, you know, if you want to help out, if you know the answer, I'm happy to hear it. So.
I'll get you next.
Hi. So one of your earlier slides showed that gravity is compressing
Mhm.
the universe and eventually creating galaxies and planets and stars. But also, as the universe is expanding, I can only imagine in my mind that how is it compressing a galaxy to form the planets, but also as the universe expands at the same time, doesn't those opposing forces, or that's probably not how it works?
No, I'll wait for getting Mike back. Sorry. Your cardio is better than mine. No, this is a very good question. So you're right. So the universe is expanding. So then how is gravity compressing everything? Well, gravity is trying to compress everything. And if there were enough material, if gravity was strong enough, the universe wouldn't be expanding. It would have started expanding, and then gravity would have pulled everything back together. And that's, you know, where you get things like a big crunch you might read about, is if there were enough gravity or gravity were strong enough. As it turns out, gravity, you know, sort of lost that fight. The universe is overall expanding too fast for gravity to win, but the denser parts of the universe that had more matter and therefore stronger gravity in them, gravity was able to win in those regions and pull things together.
So what's behind the behind the whole end of space?
Hard question.
Well, I'm going to defer to my, you know, many colleagues here who actually make observations to ultimately figure this one out. But I guess, you know, we don't know, and our best guess is that the universe is infinite, that it just keeps going. We'll sometimes talk about things like the size of the universe, but all we really mean when astronomers say the size of the universe is the size that we could feasibly see out to. And that's just because both things are fainter when they're far away, but also because since the universe has only been around for 14 billion years, there's only been so much time for light to travel from anything to reach us, which means there is a point where something's so far away that there's just not enough time for the light to reach us. So there's a limit to how far we could see, even in theory, in principle. And as best as we can tell, there's not like an edge there. There's no edge to it. It just keeps going. There's no evidence for it changing. So is it really infinite? That's a great question, but it's really big compared to even the enormous scales we can see.
Good job. Challenging question. We'll do one more here, and then we'll save the rest for our Q&A panel in just a few minutes.
So instead of asking you what you think dark matter or dark energy are, I'll put it a different way. If you could have, say, $1 trillion to say, have some instrument to get you some kind of data that would really make your life easier or reveal something new, something along the lines of like LIGO or data, like what would that instrument be and what kind of data would you be interested in?
Yeah, I mean, there's probably a lot of things I do with $1 trillion that aren't necessarily astronomy centered. But on the astronomy side, I think, unfortunately, the cop-out answer a little bit, and I know some of my colleagues hate when I say this because they're trying to write proposals for different instruments, is that I kind of, there's no one number or one piece of data. You kind of want, it's the combination of all of these in concert. But I think where you always learn the most, though, is when you're breaking some qualitatively new ground, right? It's not, astronomy, there's so many big uncertainties and there's so much new ground that we haven't explored that it's rare that we make big discoveries by measuring the same thing we've already measured better or more precisely. There are plenty of areas of science where that's true. A lot of particle physics, you measure things super precisely and that's where you discover new physics. But in astronomy, it's often by opening new windows. So something like LIGO opened a completely new type of window by seeing gravitational waves. So, something like, gravitational wave observatories at many frequencies that LIGO can't access would be a game changer. And some of those are being planned. LISA, if you've heard of it, is a plan for an array of satellites in space that'll have a laser interferometer to detect gravitational waves. But things like that, and even super network of those, things like, you can do that with optical telescopes interfering with each other, huge telescopes in space, giant telescopes on the moon. These would just open up new types of measurements that we haven't been able to make before. Each of them would give you a new window. So I genuinely have a hard time, depends on the day and the mood I'm in, which one of those I'd be actually most excited about at that exact moment. But I think it's really about thinking about what's going to break some qualitatively new ground, because that's always where the discovery is, right? And every time we've ever done that, we discover new types of objects that nobody anticipated and learn new physics from it.
Okay, let's thank our speaker one more time. Okay, so now is the point of the evening when we have a brief intermission. We're going to set up a Q&A panel in here, consisting of a speaker, myself, and 2 other members of the department to handle questions from you on whatever topics you have. We also have the telescope set up right now in the field behind us. So if you're interested in going to see those, you can go straight out the front doors and follow the signs around behind us. And those will be going until about 9:45, and we'll be going until around the same time. So feel free to go back and forth. And maybe we'll see you at the Death Valley Dark Sky Festival or Astronomy on Tap in 2 weeks. Thank you, guys.
No, it was a good question. Thank you.
Where are you? Okay. So you were far enough. We weren't the lead. I saw it. Yeah, so we're up in Sierra Madre. We evacuated the first few hours. The evening fire was on the towards us.
I'll send something out probably this weekend.
And very panicked for a few hours. And then, you always feel bad because it was like, our good luck was that the wind shifted, of course. Which means,
Hi.
Yes.
We're wanting all this video for research. We don't have resources for that's like kind of keeping kids engaged. And VR is a good way to see stuff. You can't see. There's a new stuff in the VR. Those first concepts
Oh, yeah. For different probabilistic scenarios like gravity and such. You guys know
We'll have the panel present, but I don't know because,
Sorry. Yeah, no, you're good. Yeah. Yes, I didn't know him well or anything. I was just a graduate student, but his office, the grad student office.
Oh, really?
My grad student office.
Oh, that's pretty sweet.
I did.
Oh, really?
So
That's cool.
yeah.
Big one. Probably the equivalent of like 10 million cities. Used to be about these days. It's pretty much, there's always smaller things that you can do on the clusters. The really big production ones that we.
That's okay. That's okay.
Yes, yeah, so there's, there's. The challenge with that.
I do it in all
schools.
I get confused.
It's just the gravity. There's this one. So it's not unique. Yeah. But it's still.
Thanks for
That might be angry.
that might be.
It's okay.
We haven't finalized when we start, so it's like.
Oh, okay.
Yeah.
I just.
Oh, there's perfect.
I was just, let me check if my parents are outside. They might have gone around the corner. Let me just check.
Hard to read. So,
She might want to go there.
Come on, I wasn't so pretty with it.
That's very good.
Thank you.
Go ahead and take some.
Isabel like highlighting the red.
That feels really good. Not sure how. But yeah, so, where everybody goes, and then.
Yeah.
Only No, idea. Oh, so I was working on some like SAT constraints of like so basically, there's been some like simulation, like idealized simulation of clusters.
Okay.
But then like people are like,
Together.
find some really like systems in existence. Like that are so you can just hide that stuff and try to get more like trustworthy. I mean, I haven't run into any problems. It was just like I think Vera was sort of not very satisfied with the goals of the project, but it was like very clear, like quantify what qualifies as a fully cluster and things like that.
Yeah. No, I mean, well, I
Oh,
well, it's actually. Like,
yeah, I saw that paper. There's like a third one.
Yeah.
Okay.
Okay. Well, yeah, that's the also magic cluster. Alright. Okay, easier. Please talk. Alright.
And I'm gonna hand it off to people to ask questions and then we'll.
Okay, thank you guys for sticking around for our Q&A panel. What we'll do is, just very quickly, we'll go through and introduce ourselves, talk about the science that we work on, and then we'll open it up to you guys to give us your questions, and we'll do our best to have some coherent response to whatever question you throw at us. So I'm Cameron Hummels, I'm a research scientist here, and I organize these outreach events. My research is very similar to the research. It's like a subset of the research that Phil does because he does many, many things. I primarily work on galaxies, computer modeling of galaxies in their environments and looking kind of at the atmospheres around galaxies and how that influences how they live their lives and how they're formed.
You'll just saw me talk for a while, so I'm Phil, and I work on the stuff you saw and the stuff Cameron mentioned.
Hi, my name is Isabel. I am a grad student working with Phil. So I also work on similar things, but in particular, I focus on dark matter and different models that we can simulate. And I also think about cosmic rays and also really small galaxies.
Hi, I'm Harsha. I'm a third-year grad student in astronomy. I work with Galaxies, and I study multi-wavelength probes, so I combine different wavelengths all the way from radio, X-rays, optical, and sub-millimeter to get the shapes of galaxy clusters. So I do basically everything galaxy cluster related, which is collections of galaxies. I study the domains within them, I study their shapes, also with some constraints on dark matter. So, yeah.
Okay, we've got one microphone, so I'm gonna do my best to run around to make sure everybody is heard. So yeah, questions from the audience, we'll start with you.
Hi, I just started taking my first astronomy class in high school, which is why I'm interested, but I was kind of still confused on what exactly is space-time, like what is the fabric of our universe and how can you like bend it and what does like bending it mean? Yeah.
Yeah, who wants to talk about space-time?
You
You wanna talk about space time?
I'm happy for anybody else. I mean, don't feel bad about getting confused about what is space-time and how can space-time bend, because there are, I get confused about this, and there's people whose whole career is studying the equations of gravity who get, confused about this. This is, the what is space-time is a very active question in physics, actually. Like, what does it really mean? And similarly, like, what does bending it really mean? So there's a school of thought that bending it's just an analogy, and it's just that those equations for bent geometries work to describe the motion of objects under gravity. And that there's nothing more to it than that, that it's just, a construct and it's just the math. And to me, that's very unsatisfying. Some people are very mathematically minded and that is sufficient for them. I'm a very visual person, as you can probably guess from all the movies and stuff. And so I always, imagine like analogies that probably many of you have seen of like, you put a sheet with like a weight in the center and it bends and you just have stuff roll around it. And that's how I imagine it. And there are people very actively working on trying to understand like, what does that really mean in terms of like if space-time is stretching, then what is it that's stretching, and how does it exist or come into existence? Did the Big Bang happen in space-time that was already there, or did the Big Bang create space-time itself? We don't have answers to these questions, and people are trying to come up with both theories and ways to test those theories. But I don't know if any of you have anything to add, but I think it's a really big open thing.
I agree with all that, and I have a book recommendation. It's called How to Teach Relativity to Your Dog by Chad Orzel. It's written by a physics professor, and the sort of structure is his anthropomorphic dog asks him questions about physics, and he explains it. I read this book when I was starting to get interested in physics. Actually, no, it's what got me interested in physics when I was about like late middle school, early high school. And yeah, highly recommend, and it does discuss some of this.
That sounds good. I'll come back to you.
I had a question for Phil. If gravity is Thanos, then what would we call dark energy? And also, I noticed that your movies were like zooming in from really big to really small. So I want to ask, is that from combining the FIRE and STARFORGE simulations, and what were some issues in merging the two since they're dealing with such different like situations?
Okay, I thought of this analogy earlier today, so I don't have a good dark energy character. I don't know if anybody.
No, I don't know.
Any suggestions?
He's like the Sith Lord, but that's not.
Completely different franchise. I mean, in some ways that might work because it's kind of a nobody ordered this, what is it doing here kind of thing.
Maybe
Yeah,
like,
Doom.
yeah, I was gonna say like one of the like timeline people.
Or yeah, like Kang or something, because
Yeah.
it involves, a lot of the theories are maybe it relates to the multiverse or different dimensions, higher dimensions, things like that. I mean, there's, you know, again, I made the allusion also earlier, you know, on a more scientific note, you know, dark energy, we really don't understand much about dark energy. We have a couple of numbers that are very well measured, like how fast the universe is expanding, that are fit by a model that we call dark energy, but that's really all we know about it. Dark matter, we still have a lot of mysteries, but sometimes it gets lumped in the same boat, but really we have a lot of measurements that there's something exerting gravity, and you know, dark matter, we have a lot of constraints. The problem with dark matter is that we have a huge number of models that could all explain those measurements. Dark energy, we only have a couple of measurements, and we really struggle to come up with models for even those couple of measurements. So they're kind of different beasts, and both poorly understood. To briefly answer the second half of your question, I don't want to go too technical, although happy to chat offline maybe. Yeah, so these simulations that zoom in really far between scales, that's something that myself and people in our group and collaborators and other people in the community have really been building to for many years, trying to link these disparate scales, because that's so much of the challenge in astrophysics, is everything is happening on these hugely disparate scales, and it's very difficult to model that all at once. It's also very difficult to observe it all at once. And so here we had sort of two independent projects, as you mentioned, FIRE and STARFORGE, and we built, STARFORGE was led by a former graduate student from here who I advised, Mike Prudich, and we very conscientiously built both projects for several years towards them being able to talk to each other and play nice with each other, kind of. So it was a very conscious plan that eventually we would be able to run sort of one simulation that had all of the physics that was important across scales. But one of the things you need to do when you're doing these kinds of computer models is you have to make approximations, because you can't just solve every equation for every atom in the universe. Even with Moore's law and computing, that'll never get you a solution. So the problem is that often the approximations that you can get away with on certain scales are very different from the approximations you can get away with, or the terms you can drop, right, if you've got some equations. So you have to be very careful about writing a more general form that can kind of interpolate sensibly between those limits, for example, but also isn't doing a huge amount of extra computational work where it doesn't need to do that work, because then it just becomes intractable to run these. And that's something people are still very actively coming up with new ideas for how to do. There's always new insights from folks from other fields as well. I mean, this multi-scale stuff isn't unique to astrophysics. That's a problem in almost every natural science, I think, and engineering.
Looking at questions from the online YouTube audience, but it's probably close to your bedtime, so. Question.
If stars will die and turn into black holes, and black holes keep getting bigger, and the universe is super old, why haven't black holes eaten up all the solar systems?
Why haven't, with sufficient time, why haven't black holes eaten all the stuff? Is that basically the question? I'm happy to, but I'm also happy to. You guys want to talk about why hasn't there been sufficient time for black holes to consume everything? So there's kind of a misconception about black holes that they try and eat everything around them. But really, black holes aren't that different from other massive objects. So like if you have a really massive star and you replace that massive star with a black hole of the same mass, it's not really that much more efficient at pulling stuff into it. You have to get reasonably close to a black hole, and you have to be going at about the same relative speed as the black hole in order to fall into it. And most of the mass in the universe, whether it's solar systems and planets or other stars or gas or whatever, isn't close enough to black holes that it's going to fall in. Eventually, in trillions of years in the future, we think that probably eventually stuff will get close enough to black holes to fall in. But certainly in the reasonably short period of time that our universe has been around, things are getting farther apart. We were talking about the expansion of the universe. Stuff is getting farther apart from each other, and so it becomes harder and harder for stuff to get really close to these black holes and fall in and get absorbed. So we have to wait a much, much longer time before stuff probably all falls into black holes. Yeah. Yeah.
And if you wait even longer, eventually the black holes might evaporate. This is one of the calculations that Stephen Hawking is famous for.
Okay.
If I understand my astrophysics history enough, which I don't know much of, at one point Einstein was kind of like surprised by his own calculations for black holes. I'm kind of wondering what the gap is now with like observations, simulations, and like theory.
About black holes or about
your simulation?
The general gap between theory and observation.
Like theory and like, oh, we know what it looks like now.
Okay, but not just for black holes, like for the whole universe.
Yeah, for
Oh, goodness. Okay, well, I think it's pretty dependent on the area of astrophysics. There are some things that we think we have a pretty good match between theoretical calculations and observations that we take with telescopes. And then, like dark energy is one of those areas that there's a large discrepancy because our theories can't even really explain a lot of the observations. So I think it's somewhat dependent, but let's talk about black holes. Let's pick one area since that's the one that you initially brought up. How well do our models for black holes represent the observations that we take of black holes? I mean, well, you want to talk about accretion disks?
I mean, I think there's, I think, if we're talking about the real heart of the black hole itself, then we only have a few indirect measurements because it's very, again, nothing can get out once it gets in. So we have to sort of map out what gravity is doing around the black hole. And those are things that you can predict with Einstein's equations. And it seems like every number we've been able to measure related to black holes fits with those predictions. So it seems like that works really well. In terms of our understanding of that stuff swirling around the black holes itself, it's much poorer. We have a lot of measurements, and we've known that stuff is swirling. These objects like quasars that I mentioned, where you've got a lot of material swirling around black holes, they were discovered in the early 1960s. They were recognized first by Caltech astronomer Martin Schmidt as being these sort of cosmologically distant objects and probably these giant black holes. And so we've known that there must be stuff swirling around them, but our models really aren't able to make quantitative predictions for the measurements we make of the things like the spectrum of light that's being emitted by that material. It's not even close right now, basically. It's we're trying to, the models are playing catch up with decades of observations, trying to even get in the right ballpark. But this is how the field advances. If I'd shown you, if you'd seen this talk about, oh, I wouldn't have given this talk, but when I was a grad student, if you looked at like what was the state of the art for simulating a galaxy forming from the cosmic web, it'd be really disappointing because the galaxy would look like a sort of blob. It'd just be a vague amorphous blob. And every galaxy you simulated was a vague amorphous blob that didn't look anything like real galaxies. And it's only been really the last decade, I'd say, that the models are able to make galaxies that, like one of my highlights of my career was like putting some of our fake simulated galaxies in a star field and tricking some observers into thinking that they were real galaxies. But yeah, so that's an example where there's still a big gap. I don't know if you want to.
Yeah, one thing I can, it's not simulation related, but one thing that very recently actually came up was observations related to theory. So, for example, one of the grad students here actually, as part of the LIGO collaboration, which was I think mentioned before, about the long arms that are measuring gravitational waves. So they detected this merger of black holes, and one of the grad students actually led that study, which proved for the first time Stephen Hawking's area theorem, which basically means that when two black holes collide and merge, the surface area of the final black hole is larger than the sum of the two. It has something to do with entropy. We can go on with that. But there was a first time detection of this surface area by a grad student that year. So yeah, there are a lot of, I think observations are also fairly far behind. We are, I think, catching up with, in black holes, there's so much theory development, we don't really know how to observe things as well, very much either, apart from the accretion disks that was already mentioned. So this is one way which LIGO helps us observe, which is very cool.
There was a question from our YouTube audience, because we're recording and live streaming this as well, so I figure I should get a couple of their questions. There's a question from our YouTube audience that asks, if we were to stand on the surface of a neutron star and look up, what would we see? I was thinking about this, and I don't know. It seems to me, first of all, just to make sure everybody knows, a neutron star is not a pleasant place to be. A neutron star is what happens when certain very massive stars, much more massive than our own sun, live their entire lives, and then usually it ends in some sort of supernova event for these massive stars, and what's left over is what's known as a neutron star. It's very dense. I think the densities are, it's something like the equivalent of taking the mass of Mount Everest and compressing it down to the size of a sugar cube.
I think it's 1 teaspoon is the mass of the Earth.
Oh, forget that. I was going to one teaspoon is the mass of the entire Earth. So, the question, if you're standing on a neutron star, you won't be standing for very long because the gravitational field is such that it will squish you onto that surface. But what would you see?
Yeah, I mean, again, I think again, the cop-out answer is you wouldn't see anything because you'd get squished. And I don't think you could actually have something, even like, I don't think you could put a light receptor of any kind on the surface because it would get crushed. I mean, the tallest mountains on a neutron star are much less than a millimeter in height. They're more like a micrometer in height, I think. But there's also, but it's a fair question of like, I think a neutron star is almost as dense as a black hole. It's not quite as dense, light can escape, but it's only like, if it like increased in density by just a factor of a few, it would collapse into a black hole. And so one of the things that would definitely happen, and there's people in this building who would be able to answer this question much better than the four of us who work on strong gravity and neutron stars specifically. None of us really works on neutron stars. But when gravity's strong enough, it's not quite stopping the light from escaping entirely, but it is able to affect the trajectories of the light. It's able to bend the light rays as they try and move out. And so you can get really strange effects, like some light that's moving out from one side of the planet can get bent around. So if you could actually stand up off the surface, you could sort of see the opposite side of the planet from where you're standing, from that bending the light around. So again, I don't have the full answer.
That's pretty good.
Yeah, I'm also assuming the magnetic fields would lead to very pretty displays. Anything at all?
Maybe there'd be an aurora or something.
Yeah.
Like very, very strong. So basically auroras are because of the Earth's magnetic field and all the fun particles from the sun come and come to the Earth's magnetic field, and we see all these fun colors that we've been seeing. Even in the past couple of days, there was a very, very huge solar storm, which of course we can't see from here, but anyway. So I think so neutron stars, there's a specific kind of neutron stars called pulsars, and these are the ones that emanate like really high energy jets from them, and they're spinning and stuff. So they have a very, very strong magnetic field. So I would presume that something like a very fantastical aurora display, if there are streams, if there's like a star, right, or something that would stream high energy enough particles, that would probably be one of them as well.
And for context, very strong magnetic field here means something like 10 billion times stronger than the magnetic fields we can generate on the Earth.
And if you looked down at the neutron star, in terms of like what it's made of, it's what physicists will sometimes refer to as a nuclear pasta. It's basically just a giant atomic nucleus. There's a bunch of protons and neutrons merged together, so whatever that looks like.
It'd be an interesting experience for a very short period of time. Additional questions?
So I had a question about the dark energy. So the DESI 2025 survey, so this is like just a question out there to see what your guys' thoughts are for the whole panel. The evolution or the thought of evolution of dark energy is predominantly like changing the avenues of how simulations would look like in galactic and just evolution of our universe. So how would you guys begin to estimate this evolution of dark energy? And how would this be implemented in our simulations? And, you know, what can this tell about the beginning or the Big Bang, like just what we know of our evolution of our universe today?
So how would we,
Just begin to estimate because it's
like
the
how would
range
we
of the
parameterize
Yeah.
the dark energy? I mean, we can parameterize the dark energy. In terms of its force on its expansion, its change on the expansion rate over time. Because the universe is expanding, the stuff is traveling away from us, but that rate of travel is changing over time, in part because of this additional energy term. So we can parameterize that, but it's not very well constrained. And there's a number of different telescope missions that are trying, like Euclid and SphereX at some level, are trying to better constrain what this expansion rate is and how it changes with time. But at least
Yeah, so this may not answer exactly your question, but so in terms of understanding this DESI result, for context, the assumption for decades, so the Nobel Prize for the discovery of dark energy was, I think, in the late 1990s. And the assumption was it was a cosmological constant, a value that's fixed in time. But this recent experiment called DESI showed that it actually seems to be changing in time. And that'd be a very exciting result because it would violate what we call the standard model of cosmology. So there's two things that could be happening here. One is there's some type of systematic where we have these different data sets that we use to try to figure out the value of this constant that isn't a constant. And it's something in the astrophysics or not understanding the measurements. What I personally think is more exciting, although probably less probable, is that there's actually exotic physics. So that would be something where you could just have a time evolving dark energy, And that would be something that we could try to parameterize and put in the equation. Or there's been some particle theorists who've shown that if you have some type of dark matter that has an additional like astrophysical or cosmological range interaction, essentially additional gravity, you could create something that looks like this signal from DESI. That's actually something I'm working on simulating. So I'm very excited about that. Selfishly.
Okay, additional questions.
This is probably similar, like, I was wondering, how do you collect, and there's a lot of observations you said, like, within the last decade, or maybe even like 50 years, but that's like a blip of time in terms of the cosmological scale. How do we collect enough data to actually be able to model, something as complex as, the creation of galaxies? And then as the universe is expanding, we're probably collecting less data. Like it's slower, it's slowing down, right? So, like, how's that?
Excellent question. Who wants to talk about?
Yeah, it's a very good and important question. You know, how do we actually talk about the evolution when, as you said, the timescales, you know, even if we have historical data sets that in some cases, for some examples, might go back even hundreds of years of historical observations, sort of pre-modern astronomy of some things you can see with simple telescopes. You know, even hundreds of years is a blip compared to the timescales over which the universe and galaxies are evolving. So effectively, it's one instant in time that we're observing. There are some things that change on human observable timescales. A supernova explosion is one of them. That thing turned on, brightened, and decayed. That supernova I showed in M82 over a human observable timescale, over a matter of days and months. But a lot of these other things, the background galaxy looks perfectly identical. I mean, that's how you know that a supernova went off, because the rest of the galaxy hasn't changed at all in our images, and then suddenly there's one bright spot. So what you have to do are a couple of things. One is that we're very lucky in that the universe, you know, many of you have probably heard some version of the universe can act like a time machine, because as we look at things that are further away, we're looking back further in time. And that is a key part of it. We look at galaxies that are more distant. It took their light longer to reach us, which means we're seeing light that was emitted at earlier epochs in the universe. And we're now able to push back to earlier and earlier times. The galaxies being discovered by the James Webb Telescope are emitting that light that is now reaching us and the telescope when the universe was only roughly 100 million years old, as compared to 14 billion years old. So we can map out how the populations of galaxies differ at different times. And that key word there is populations. The other thing we use is we use statistics, and we hope that we can link snapshots, so we can have many snapshots of galaxies, let's say nearby us, that are doing different things. And then the trick is to come up with, using things like these simulations, a story, a model that tries to link them in some evolutionary path and say, okay, this galaxy looks like what would happen if you took this galaxy and did this to it. And where's the in-between? Well, that would look like that galaxy, that kind of thing. And then, of course, you have to try and come up with tests for, is that really the origin of that type of galaxy? And that's a lot of the back and forth between observers and theorists in this field, is that kind of thing. I don't know if Harshit wants to.
Yeah, I think Bill covered all the points. And I think one thing to really that struck me the first time I thought about this exact same question is that even though we have, in addition to having this time snapshot at different distances away from us, we have a lot of variety around even in our nearby universe. So, for example, if you think about things like stars, there are lots of places even in our nearby universes where stars are actively forming. So we can look at these star forming regions and see what's going on. It might be just a blip of time, but there's so much diversity in what we can observe even in our nearby universe, whereas Phil said you can basically snapshot of like, oh, this galaxy is what would have happened with this galaxy 300 million years later, because it's much more advanced in the state of evolution and so on and so forth.
I have a follow-up to the trillion-dollar question that you were asked. And it's really to help answer a question my daughter asked me, because she's starting to learn astronomy, and I'm like, I don't know about physics. So, you know, the trillion-dollar question, you can't do the research without working with a group of folks that have different skill sets. So, you know, in the research that you do, you know, what is the role of the physicist versus the astronomer versus maybe the engineer? And how do you work together to solve or figure out these questions that need to be answered?
Let's talk about collaboration.
So one thing I personally have experience with is I am part of a collaboration group called FIRE. So we just launched our telescope. It's now in space. It's doing great. We made our first all-sky map very recently. So FIRE was one of those things where I actually got to see the whole process from start to finish, where it was like tens of years of firstly, the first thing is the scientists think, the physicists who would like experience what kind of data sets you need, they sit and they think, they're like, oh, this is the kind of data that we need to answer this specific question. Then they talk to the engineers of like, what kind of instruments can get us this data that you need. You submit a proposal. Hopefully NASA gives you $1 billion for that. If NASA gives you $1 billion, then you can start to give money to the engineers who actually procure all the elements and start building the telescope. So the engineers are mostly foundational in basically keeping us on track of like, this is what we can achieve, this is the materials required to achieve it, and these are the things that can go wrong. So they built the whole thing with, I think, during the actual building, there's very little input from the astronomers, actually, and also physicists. And then it's finally built. It goes into space. That's all the engineers going into space. Deploys in space. When Spherex basically opened its eyes and we saw the first lines, it was all the engineers who like started yelling because they knew that those lines were precisely what they were expecting. And we physicists were like, why are you screaming? So we had no idea what was going on, but they know exactly what first line is supposed to look like, what lines we're supposed to see, what deployments to do, how to protect the sun from coming into the field of view and frying the telescope and so on and so forth. And I think the physicists are at the next stage. Physicists, astronomers, I think I use them interchangeably. That doesn't really, with a mission like that, it doesn't really matter. They come at the later stage of actually trying to understand what the data means and what it's giving us and do science with it.
I was just gonna add, there's, we get taught this, scientific method in school that's obviously a simplification and things are messy, but it's more of a cycle of constant back and forth with all of these people interacting. Sometimes theory makes predictions or physics makes predictions that are far ahead of what we can measure, where, I've made predictions in papers, and I think the other theory people have here too, that, oh, we would need a telescope 1,000 times bigger than anything we've got in the sky to make this measurement. But, maybe someday that'll be interesting, maybe not. But a lot of times the advancements are really driven by technologies, right? Whether that's, and that directly manifests in the theory enabled by computing, but also the theory is driven by new discoveries, and those discoveries are fundamentally ultimately driven technologically by being able to reach into new domains, basically. And it's always some new technology at the heart of it that enables you to make new types of measurements. You look at exciting things that are happening in X-ray astronomy right now. We're able to make new types of measurements that we couldn't make because people were able to build new types of detectors on satellites that can make qualitatively different measurements than we were able to make before. So that's always happening. And I think one other answer to this question that wasn't mentioned but is important is, astronomy does require collaboration in the sense, not just in the technology side and building and observations theory, but also it's an intrinsically interdisciplinary field, because there's all the things I described are what we call multi-physics. There's lots of different things happening all at once affecting those systems. It's not, you can't, and it's not like some laboratory, a lot of laboratory physics, you try to boil the problem down to like the minimalist thing, the one bit of physics that you're trying to understand or test, or the one equation or the one interaction. And I'm being a little oversimplifying here, but that's true of some areas of physics. And I'd say astronomical systems, we can't do that. It's not a laboratory science. In some ways, we're more analogous to maybe biologists, where we're studying complex interacting systems that have many parts to them that we can't entirely control while we're making our measurements of them.
I want to be an astrophysicist because I have a lot of questions. Did becoming an astrophysicist answer all your questions?
What, you mean, when we became astrophysicists, did we answer all of our questions? Is that what you're asking? I wish. No. I mean, we can start to investigate some of those questions that you may have or that we may have, and what you saw tonight in the presentation are some ways in which we've investigated those, but there's still a lot of questions out there that remain unanswered. But maybe you can be the one to solve those problems, so keep pursuing it. Additional questions?
Hi, in the last 100 years or so, we've been powered with fossil fuel, coal, solar, wind, geothermal, nuclear energy. In the last 20 years, the science world has made incredible discoveries. Research it seems like it's just exponential. There's tons of, or there's many more space telescopes or a bunch of arrays of telescopes being built on the Earth. Do any of you feel that, let's say, the next 20 years, there's going to be a point where a discovery is going to come, where there's going to be another form of energy that mankind, is it going to be at the is science world going to do it at the university level, or is it going to be more likely that some private company is going to have $1 trillion and do it themselves?
Provocative. A new form of energy discovered. I mean, at some level, the dark energy might be a form of energy. The Department of Energy is investing in many of these studies that are trying to better understand the nature of this dark energy to see if it could be captured, if it could be manipulated to produce them. But also nuclear fusion is an energy we know about. It's what powers the stars that we see in the sky that Phil was discussing tonight. And thus far, we can't really produce controlled nuclear fusion reactions here on Earth. But if we could, and this has been a goal of physics for the last 70 years, if we could produce something like that, it would effectively be, free energy, because you can use hydrogen, which is the most numerous abundant element in the universe. It's found in water. You can take water, break it into hydrogen, and use that to create nuclear fusion reactions that would be extremely powerful. And if we could control them, it would be, basically energy for free. So that is certainly one area. But you were talking about like a new area.
Well, or that, I guess, if I could follow up, I guess maybe what I'm asking is it a priority, or is it one small part of space exploration, things like that? Is it a small part, or is it?
You mean what's the priority of like
developing. new
international
energy.
science.
Well, developing new energy, what we have now will probably eventually run out.
Sure. I don't want to.
Well, I think it's a huge priority for a lot of scientists. It depends on the field and what they're working on. You know, as you know, I'm sure, you know, there's people who are very focused on some of the challenges of specific forms of energies, you know, like, and some of that's on the private side, some of it's on the academic side. You know, there's a classic cycle, and again, it's always messier than this in detail, but a lot of these, some of the early breakthroughs in conceptual development might have happened on the academic side where there wasn't a clear commercial application. And, you know, something like photovoltaics is a good example of that, and solar power, where, you know, a lot of the breakthroughs initially happened in academia, but then there was a lot of progress, and what's made it, you know, boom has been you know, improvements in the cost efficiency, and which are, you know, an engineering problem, and a lot of that's been led by more the private sector side of things. And I think, you know, you need all of those working together. Certainly there's, you know, colleagues in physics who are very interested in this question and worked on it. And certainly there's interest from the astronomical side, both in, you know, maybe we will discover something about dark matter or dark energy that will enable a breakthrough. I think it's hard to say right now whether we will. And also in terms of application, I mean, I think the thing that would be I think this is a point where by far the most transformative thing, if we had qualitatively revolutionary energy technology, you know, orders of magnitude better than what we can do now, the thing as an astronomer that immediately comes to mind that could potentially enable that's sci-fi right now is something like interstellar travel or something like that, right? Which, you know, the practical barrier to even getting to the outer solar system for us right now is the energy constraints and costs of doing it.
Right, there you go. Okay.
So Hubble photo, the astronaut called Cloud 9. It's a starless gas-rich dark matter cloud, and the scientists there call it, well, the scientists call it a filled galaxy. What can we learn about the early universe formation and dark matter from these objects? And how does this observation guide your current research?
I haven't read this paper. This is Rachel B. now.
Yes, I know. Do you want to say?
Have you read it?
And then how about you go first? I also have not read this paper.
All right, so apparently I'm the only one who's been. But we're all aware of it, but Phyllis hasn't read it yet, but that's okay. I think it's a really interesting discovery. I think it's still one of these things where I think the community's not 100% convinced that you know, this thing is real, and it's not that there's any flaw with the paper, it's just that this is a really challenging measurement, and we're going to need follow-up measurements to really confirm that this is real and what it is. But it's a prediction for a long time that there should be these dark clouds of dark matter, that the smallest dark matter structures that I was showing in my talk that form in the cosmic web, they basically have so little gravity that they're not able to trap enough mass of gas that it's able to get dense enough to form stars, which is what would light them up, basically. And so if we can really detect these dark halos, these dark balls of dark matter, things that have a lot of gravity but don't have any visible stars or luminous matter, normal matter in them, this would really be we have many validations and tests of the dark matter model, but still people keep trying to come up with, is there a way to avoid dark matter existing at all? And you know, the most popular way for decades has been, you know, is there some way to modify Newton's or Einstein's equations of gravity that we can avoid dark matter entirely? And you know, most astronomers don't think that's a viable way forward because almost all of the attempts to do that haven't worked. We've tested, you know, people have come up with ways to do it, and then you test that, it makes predictions, and those predictions fail, where the simple dark matter model that is just some invisible matter seems to pass those tests. But the most glaring signature of this would be the confirmation of these truly dark objects. So it would tell us that, you know, more than anything, there has to be some dark matter, because if there's no regular matter, then it can't be just that the gravity from the normal matter is different, because there's no normal matter there to be exerting that gravity, if that makes sense. So I think that's a really important thing. And we could learn a lot potentially about the dark matter from how, since it's a sort of pure dark matter object, you can get a much cleaner sense of how it's clumping and how it's interacting with itself, basically, from those types of objects. But right now, it's just at the threshold of we think we may have discovered the existence of one of these. And there's going to be a lot of follow-up measurements to try and characterize it to get at exactly the question you asked.
Kind of a related topic is 10 years ago, there was an observation that was kind of the reverse of this. It was a galaxy that didn't have any dark matter around it. And again, this was controversial when the first papers came out. There were follow-up observations, and now I think it's pretty widely accepted. And it turns out what happened in that case is, so as we see in simulations, we have these clumps of dark matter, and then the galaxies form inside of them. However, if you have like a larger galaxy and like halo of dark matter fly by, it can strip the dark matter in the other galaxy from tidal gravitational effects. So these like dark matter deficient galaxies have had all their dark matter stripped away. Yeah, so the point is, like, yeah, all these types of observations take time to be accepted if they hold up to scrutiny. That's a part of the scientific process.
But it's exciting.
Yeah, no, it's exciting.
All questions? Let's see what I did.
Question regarding the cosmology, the standard model. Can you describe like where it experiences struggles right now? Like I know there is a struggle with the Hubble constant, like the rate of expansion. But can you give a little bit more details about that, where the struggle comes from? And the second question related to that, as I understand, there are a lot of cosmology models. And the standard model kind of won because cosmologists, they have a set of tests, and this expansion rate is essentially just one test that is failing right now, like, and so can you also give a perspective of like how big the struggle is?
So the question is about something known as the Hubble tension, which refers to, there's something called the Hubble constant that describes the expansion rate of the universe. And the Hubble tension is that there are multiple ways of measuring this expansion rate, some of them based on how quickly things seem to be moving away from us nearby, and then others are using things like the cosmic microwave background that Phil referenced, that are looking in the very early universe, at very large distances, and how quickly things were expanding, how well we can characterize the expansion rate from those observations at very large distances. And for the last 100 years or so, up until maybe the last 5 years, the error bars on those two measurements were large enough that even though the cosmic microwave background and other large distance ways of measuring this expansion rate gave you a value of 70, I forget, is CMB lower or higher?
Lower.
It's lower. So like 68 units, I'm not gonna, kilometers per second per megaparsec, but 68, whereas the nearby ones gave you something like 72. And it used to be that the error bars were so large that they were in agreement roughly, because it was 68 and 72 are pretty close to each other, plus or minus a few. But more recently, these measurements have been made to increasing levels of precision, that they actually are significantly different from each other. So 68 plus or minus 0.5 kilometers per second per megaparsec, and then 72 plus or minus 0.5. Now all of a sudden there's a tension. These things are measuring two things that are different within there. their uncertainty values. And so that's what's leading to these concerns that there might be something wrong with the physical model that we have for the universe, the standard model, lambda CDM, or I think more likely it's that there's some sort of systematic value that we're not accounting for in the interpretation of these values that is skewing one in a way that we don't expect it to. But that's the easy way out, because then we don't have to throw out the entire cosmological model that works for many other things.
Yeah, just I add on that, in terms of, it really does depend on who you talk to, how significant people think this is, because it's very significant in a statistical sense, as Cameron was saying, but it's much harder to know if there's some subtler calibration error or something like that that is giving you these, we're only talking about a few % bias in your measurement, and when you try to measure things that precisely, there's a lot of things that can enter into the final number. And so what people are trying to do that might not show up in your quoted error bars, are we really, fundamentally this is a question of how accurate are those error bars that people are really quoting on these measurements. And I mean, people are working very hard on trying to come up with completely independent ways of measuring these numbers to get at that. And as you alluded to, there's many other tests as well. I think one thing that is interesting is some of these, the Hubble tension in particular, there's a sort of interesting history in astronomy of that number, where, as Cameron said, the error bars used to be much larger, but historically there was a period of a few decades where there was a big debate about what the number was, where one group was measuring about 100 and one group was measuring about 50. The people pointed out that scientists aren't immune to confirmation bias and sociological biases, and it was pointed out by a couple of people in the field that the best predictor of whether you measured 100 or 50 in this period was who your PhD advisor was, rather than the technique you used to measure the number. So eventually it was realized that there were some calibration errors on both sides, and the number kind of collapsed to about 70, halfway between the two, actually. So I think the community is kind of, especially with that specific memory, there's some of the communities like, is it just going to collapse to halfway between the two again? And neither one was really right, or is it going to turn out that one side was right, or is it going to turn out that there's some, interesting wrinkles to the standard model? And there have been other challenges, just to briefly mention, to the standard model, like this DESI measurement was mentioned, which would entail some revisions to that standard model as well. The standard model for cosmology is a lot, we attach this term standard model by analogy to particle physics. The difference is the particle physics standard model has withstood, millions upon millions of tests, measurements up to, 12 digits of numbers and predictions from it. The cosmological standard model is by far the best cosmological model at reproducing data that we've ever come up with. In the sense that it can reproduce some numbers up to the second digit, basically, but it's a lot less.
It's hard to make precision.
Yeah.
Just to add real quickly, as recently as 2025, I've been in conferences where people were yelling about the value of the Hubble constant at each other.
I really quickly wanted to address one of the questions from our online audience. I don't actually have the answer, but maybe one of you do. The solar storm that we've recently been experiencing over the last week or so, the question was, is there any knowledge of whether or not this has damaged any of the equipment in orbit, like satellites or anything like that? I'm not aware of any damage to electrical.
There was expectation because it was supposed to be extremely strong, but then something flipped, and I could go into the details of some of it, but it's basically something flipped and it started to diminish instead of keep going stronger. But the original prediction was if it kept going stronger, it would be like wrecking havoc on satellites and communications, but nothing was damaged.
We could probably take one more question from the chat. He's got his phone out. He's
prepared. Thank you. This is about the simulations. I was going to ask if there's diminishing returns on the level of detail in the simulations you run, and how you compromise to run on the hardware that we currently have.
Diminishing returns.
Well,
yeah, I mean, we can all talk.
yeah, I mean, we're all familiar with this, so we all kind of chuckle because we've all dealt with this to varying extents. And yes, there are diminishing returns. You know, or at least there's, not quite exponential, but massively increased cost with each increment of improving the resolution or the amount of physics fidelity in the simulations. So you do have to think really carefully about what you need for the question you're trying to answer to fit it in. And you know, there are problems where we know we don't have enough numerical resolution or computing power to really push to the level of detail we would need to fully model something. So you have to make approximations, and this is true in all computational fields. So pretty much any fields, this is true in a million different engineering and science fields. You always have what we call our subgrid scale models, which is everything that is too small scale or too tiny or too messy to explicitly simulate on the grid. You put in some fudge factors or other representation of that, and you try and calibrate those either to other data or other simulations, but you can't do everything all at once. And we're always trying to maximize what we can get out of the hardware. One of the challenges for those of us doing simulations in the last decade plus has been the direction in the hardware is clearly for a while now been towards things like GPUs and lots of coprocessors and things like that on individual boards and things like that. And so I don't want to get too technical, but I'm happy to talk. But the thing is, this is very different from, for a long time, things like Moore's law applied to how fast a computer could do the same calculation, how really things like clock speeds of a computer, which meant, again, for those of you who don't care about the details, it used to be that with hardware advances, you could take the exact same simulation or code and wait 2 years, run it on a new computer, and you get the answer twice as fast. Nowadays, if you want to leverage continued advances in computing, you have to update your code to be able to share the work, parallelize, spread it among more and more coprocessors or processors or unit or GPUs, things like that, in some efficient way. And there are problems that are good at that. Well, this is why a lot of these platforms are being sold for things like AI, because a lot of AI algorithms, a lot of machine learning algorithms are good at doing that. Everything I showed, I think, of the simulations is especially terrible at that. And so it's a real challenge. I can't control what chips, NVIDIA is investing in developing. I have to just follow the trends in the technology. But yeah.
This is maybe a slightly different point, but one of the things that I've had to accept as a student who uses simulations is we're never going to reproduce a perfect replica of the Milky Way on a computer. We're just not. Like, we can get close to the Milky Way in terms of like the simulated galaxy's mass and the number of stars it has and maybe how old those stars are, but there's always going to be things that are different, and you have to figure out how to map that onto what we actually observe.
One other thing that I would like to add is that I think with increasing complexity that we would want in our simulations, I think we've gotten really good at like getting around it, because there are like some things of like this would take literally a million years to run on this computer, and we would spend all of the I think it's dead.
Yeah, it did.
All as a screen, all of the water in all of the Earth's lakes to simulate this, and it's like not worth it. So one of the things that we do is, for example, as Phil said, depends on what you care about. So if you're trying to really model a high resolution galaxy within, say, a cluster of galaxies, you don't try to be very high resolution everywhere, which would drastically increase your computation time. You just sort of like
do like broad gridding everywhere else and sort of really hyper-focus on this one galaxy. So I think through multiple years of simulation and development over simulations, I think astronomers have gotten fairly good at dealing with what we've gotten and extracting information from what we can within sensible runtimes.
Also say you can, in any application, you can always optimize better if you know the problem you're trying to solve very precisely. And so, people do constantly come up with new algorithmic advances that have enabled this. And in fact, if you chart a lot of these types of simulations, if you look at the resolution over time, the sort of the scaling time scale, we've actually been able to beat things like Moore's law, largely because of algorithmic advances, where people come up with clever hacks, and again, that's often problem specific because you can't do that in total generality. Usually, it's because okay, I can get away with this approximation for this problem that I care about.
My boss would say, it's 10 o'clock. So let's thank our speaker and our panelists. As I mentioned, we do these once a month. I haven't yet set the date for the next one, but it will be at the end of February. I'll announce that soon. Our next Astronomy on Tap is in 2 weeks on February 9th. And the Death Valley Dark Sky Festival is 2 weeks from today, February 6th through the 8th. So maybe you'll be able to join us for that. We'll be back next month. And if you didn't get all your questions answered, we can come up with Astros as we close down. Thank you very much.
There's stargazing at Griffith Observatory tomorrow.
Stargazing at Griffith tomorrow. Okay, thank you guys.
Thank you.
Thanks everybody for coming out.
Yeah, they do.
Well, that's like a brand new. Just got
You were mentioning this here at,
Yeah.
I got a little help in.
Oh.
Lori.
Nice.